Oh, hold on. Okay. Excuse me, I gotta look off screen because I'm looking at another screen that's over here. Okay, Susan Sherwood has directed the Center for Technology and Innovation since 2003. She is a veteran of Kuwait Museum of Islamic Art, the New York City Parks Foundation, the Scientific Center of Kuwait, Robertson Museum and Science Center, and the U.S. National Park Service. The overarching question the center seeks to answer for Central New York is how, uh-oh, my screen just went blank. Oh my God, it just went weird. Hold on. Why did that happen?
Something to be said for paper.
Okay. All right, the overarching question is, how did so few people invent so much? Understanding this legacy will help inform initiatives to engage the community's future innovative prowess. Ms. Sherwood coaches a group of volunteers, including retirees and hundreds of BU students each year, who curate, quote, stuff like memories, mementos, and artifacts, and who return technological equipment to life at Techworks, a startup being developed as an experience destination with artifacts in action on downtown Binghamton's waterfront. Can't wait to go there someday. The center's work has been recognized by an award from Computer Conservation Society UK and Google UK, and partnerships with Bingham University, SUNY Broome Community College, Broome Tioga Bose's Computer History Museum, California, Cradle of Aviation, Long Island IBM Corporate Archives, and the Smithsonian Institute. I'm so happy to announce and introduce Susan Sherwood.
Thank you very much. You took the long form. The short form was
No,
easier.
it was the medium form. She sent me 3 lengths of bios. I took the medium.
Great. Well, I'm delighted to be here tonight, and we'll see if we can get all the technology to work. Binghamton is very close to the edge of an internet desert. So, but in the evening, we're usually better than downtown. So, but thank you very much for inviting us. And I think you met one of our board members, Frank Hughes. He spoke to you in January, and he's a really vital force in what Techworks has been able to do in the last few years, and several other people. But I like to think of myself as a player coach. None of this happens by individuals. It's all a team effort. And my job is partly to try to keep the frogs in the basket so that we can all keep moving in the same direction. So I think I can switch to a PowerPoint and then do a screen share. Uh-oh. I'm now in the PowerPoint. How do I screen share first? Screen share first. Okay, hold it. Oh, share.
You can share the screen or the window.
Got it. I was doing it in reverse order. My fault. Okay, so just very quickly, our mantra is experience, innovation, past, present, future. And here's our welcome to Techworks, where questions lead to ideas. We are open now by appointment, just to conserve our volunteers, because we're an all volunteer organization, and nobody needs to get sick. So if you want to come visit, just let us know and we'll be there. So that's a really simple, straightforward a process to send an email or call us up. But in the meantime, as you pointed out, how do so few people invent so much? This is a map of the inventions and the kinds of things that happened within a half a mile of our location, including Rod Serling's father's markets there on the lower left, the first flight simulator on the very lower left, and Bundy time clocks, which is the forerunner of IBM, is at the very bottom. But if you go up, you'll see a lot of other very interesting pieces of technology that have laid the foundation for the 20th and 21st century. And we're going to focus on the space-oriented piece today. So if you have any questions, feel free to ask. I grew up in a huge family. So I'm not accustomed to being able to complete more than a few sentences without being interrupted. So do feel free. You're welcome to ask questions at any time. There may be questions I can't answer because I'm a generalist. I help put these things together. I don't necessarily do the details, but we'll get you in touch with the right person. So, okay. Part of our outreach is to the community and to the teenagers. We start to teenagers and go up. This is a Scribbler project. The Scribbler teaches kids to do Python. It has you put a Sharpie in it and it'll draw. And so we think it's important for kids to learn job skills, and this is a good one. And this is one of our BU students working with students from East Middle School at Binghamton. Just tried quickly. From the IBM piece, this is kids printing a custom banner from a printer that came out in 1964. It's the printer designed for the IBM 360 system and put together and brought back to life. It took us 3 generations of IT people, the original designers in their 80s to make the mechanics work, the guys in their 60s and 70s, like you see in the middle here, to do the 21st century hardware, and then the Watson School 20-year-olds to do the software, which is sub microsecond software, rather than doing it with the hardware that was done when it was originally made. So this is the Vintage IBM Computing Center. We're one of a handful of places in the world that has the chutzpah to try to make these old things work. So come on up, you can punch cards, you can do banner prints. Almost everything you see here is working or was working at one point. Another piece, I will tell you, we were flabbergasted. What the kids like more than anything else is the typewriters. You talk to them about Apollo, they're like, roll their eyes, but they love to type. They like to do their own stories. And Rod Serling is a native of Binghamton. His father's market was a half a block away. And when I gave a walking tour once, and one of the people on the tour said, best pickles in Binghamton. So anyway, imaging is a really important piece of this. And here's on the upper left, you'll see a girl doing 3D imaging with a Civil War era stereoscope. But they also come to see that that's exactly the same technology or same optics as your virtual reality headsets. It all works the same way. So here's 2 of our current BU students this semester. Erin's they're both freshmen. Erin is by the printer controller, and on the right is Renee, and she's holding a pigeon as part. It's a stuffed pigeon, taxidermed pigeon. One of the earliest views from above was pigeon photography. In World War I, they would strap small cameras to pigeons because as they return home, they fly at a constant rate of speed. So there was an early GoPro or spy photography, but in World War I, they used pigeons. In World War II, they used airplanes. But that's Erin's project this semester, which brings us then, we're kind of working our way, looking at the stars. We're going to look up. Some of the earliest color photographs of deep space were taken with super Ansco chrome film, which comes from Binghamton, New York. And we're slightly proud, actually very proud. They tried Kodak film. The people at Mount Palomar Observatory tried Kodak film. They couldn't make it work. So they ended up using the Ansco, super Ansco chrome from Binghamton. And this is a link here to a slideshow. They just recently put up a new blog post on William Miller and his advanced work on the first color images of deep space. So this is our latest project. This is a 10-foot mural, another William Miller photograph on Ansco chrome from Mount Palomar. And it's a nebula. So Disney Entertainment refused to let us use to infinity and beyond. They said that that was copyright. We could not use Buzz Lightyear. So now we started with Where Stars Are Born. So we think that that's a kind of a way to attract passersby and kids and the next generation to get excited about exploring space and looking above and looking beyond your particular neighborhood. So that's this most recent version. But another use of these photographs from the first series of deep colored deep space photographs were here in Star Trek. So those two photographs you see on the Enterprise console are photographs taken by William Miller at Mount Palomar with film from Binghamton, New York. So there you go. And the next person to use, traditionally we think the next person to use Ansco film in space was John Glenn, and they converted a camera so that he could operate it with his gloves on. And he did say, as a piece of trivia, that the most difficult part about photography was changing the rolls of film.
Yeah.
So after that, the next Ansco built them a camera with really large magazines. And after that, the astronauts flew with Hasselblad cameras and really long rolls of film. But here's John Glenn. There's a photo of his camera, and then one of his early photographs where you're looking down. And so it's supposed to be looking out, you're looking down. But the thinking is that some of these early photographs of the space of the Earth helped inspire the environmental movement and Earth Day. But it turns out you always have to look at some different, you have to look at all the sources. This just came from Lloyd Bostwick, who is a senior chemist at Ansco, and reading it says, Ansco products have been used as follows. And the first photographer to use Ansco film in space was Primate Ham. Astro Chimp Ham on Mercury Redstone #2 in January of '61, he was flying with Super Ansco film in the Earth Sky camera. So it was not a human, but it was a photographer, and it was filmed from Binghamton. And then you see in the bottom left is John Glenn about a year later. So Ham and John Glenn, the two first photographers looking down from, okay, and there's Astro Chimp, and there's the camera that he used, the Earth Sky camera.
Did the monkey actually trigger the shutter?
Yeah, good question. It's got a red, it's a good question. It's got a red thing, you can see a button on it. He was trained to do that. And the people at the National Zoo say that, or where he spent a good part of the end of his life, he would spend all day poking at the buttons. He had imaginary buttons that he was poking at. So he remembered what he was trained to do. So I don't know, but I don't know the answer to that question, and he's not around to ask anymore. So okay, so I'm just gonna, can you see this here? Can you see me? I'm sharing screen, so you can't see me, right?
I'll see what I can do then.
All right, I'm showing a book that's called A History in 50 Objects, Apollo to the Moon, put together by the Smithsonian. And they recognize of those 50 objects, 3 come from Central New York State. John Glenn's camera, John Glenn's film, the Saturn V Instrument Unit, which is essentially the navigation piece to get to the moon. And that was designed and built in IBM Owego. It's 22 feet in diameter and not something you're going to put in your pocket. And the third item they talk about is the Apollo mission simulator. So this is a full mission simulator. The most famous simulators you see in movies are the ones where they're spinning around or they're hopping around, you know, they're dropping them like a bedstead. But this was the primary simulator that the astronauts used. The Mercury, and this is for Apollo, but the Mercury version of this, oops, we're not going to, okay. The Mercury astronauts spent 4,000 hours in the Mercury simulator. But this all started, the brown in the back is the classroom for the command module. The green in the front is the classroom for the lunar module. And in between is what's called the mission effects projector, which we'll see close up. But that was for the landing, for using models to land and ascend and descend to the lunar surface. The way I think you want to think about these is, this is 5 years before Pong. So all of these optics are wrapped around the outside of the space module. because it is no digital there are no digital imaging and no digital graphics at this time. And pretty soon it's going to tell me to go to our video, but just really quickly, flight simulation in America was invented down the street from Techworks, with Ed Link sitting on a bellows from his father's organ factory saying, "This feels like flying." So he put together a simulator known as a blue box, where the motion system was pneumatically controlled. And it's really remarkable that he took almost completely musical technology and made it into a flight simulator, which then changed the way that people thought about planning, testing, being able to try something out physically before they actually did it. Here are 3 generations. The 1940s. The 2 blue are from the 1960s. At this point, they have solid state technology. And the orange in the back is run with the equations of motion are in software. And for the efforts that the team made to get these all working again, that's what they won, earned the Tony Sale Award from Google UK and the Conservation Society of the United States. And the team is justly proud of this. There's 6 of these in the world, 2 in the United States. 1 is in the Computer History Museum in California, which they won for restoring a computer that was designed and built in Endicott, which is right down the street from us. So we had to go elsewhere, and the team won it for the Link projects. So, but that get us to get us to space is this is an early celestial navigation trainer, and here's a Sky and Telescope article about it. And above, and if you look carefully, you'll see 2 heads and a spacecraft underneath, and that flat surface that's almost a pentagon is a simulation of the surface. Look at it. There's the sky dome, and the way the stars were simulated is they put small flashlights into chicken wire. So this is a giant dome of chicken wire with flashlights to have the constellations. And that dome will move to represent the right season and the right time of day. So we can go back a second, I think, and you can perhaps see the man's face sticking out at the bottom of the dome. So he's in the airplane simulator. And this photograph is the physical dimension. So you can see the dimensions of the celestial navigation trainer. Looks like a silo, and there's some cars from the 40s to give you a sense of scale. And we are desperately, yeah, go ahead.
Can that be made for any latitude?
Yes. You
Awesome.
just rotate, they just rotate. If
right.
I had a pointer, but it's essentially gimbaled. So the whole dome of stars can rotate for seasons and for latitude. And I'm actually, now that I think that, I'm pretty sure it can be done for latitude, but it should be able to in principle. Let's put it that way.
It looks like it because there's a curved thing above the dome that looks like it can move up and down on.
Right. So the whole thing could move. One of the gentlemen who worked on this in the 1940s, who was on our board, was convinced that if we were going to find one of these, it would be in England. And the British Air Force, or the Royal Air Force, was very happy that the ability to learn to fly at night, which is what they used this trainer for, was partly what helped them survive the bombing attacks during World War II. This is this is the Celestial Navigation Trainer in Binghamton, which is no more. So now we're getting into the Apollo or the NASA era. This is the Gemini simulator. You can see the computers behind it, but it has no visual system. They're learning here to essentially drive, to operate the levers and the equipment, and to learn to maneuver their spacecraft. Now we begin to get into the visual system, which is where the stars come in. And you'll see, and on the right is the first that was done for Edwards Air Force Base. So that was an Air Force project. And the one on the right is for the Lunar Module, which is a NASA project. And there was some interagency disputes about turf, and I have no idea, except that NASA won. So the celestial sphere is a star ball. So that's taking that dome that you had and turning it inside out. So a celestial sphere is completely flat black, and embedded in it are ball bearings. And then they're lit from there. And the light then bounces around on beam splitters, which divide the light 50 and 50. These are, and then the curved mirrors collimate the light. So it's a combination of a collimated 3D visual system. And at some point, it's going to tell me to go to the video. Jack, just a second. So all of those are built into these devices. That's why they're so huge. Oops. All right. This is where I'm supposed to tell you, Jack, to switch. And if you could please show the video. Oh, wait a minute. Maybe I'm wrong. Just really quickly.
Go ahead.
And I did. Yeah. This is a book that we've asked the guy who was in charge of the math to write this up. He's done a remarkable job. The challenge is of how to calculate the equations of motion. The challenge is every time we ask him to proofread it, it comes back with 30 more pages of new material. But this will give you an idea of the complex nature of what he's talking about and how it works out. And there's one of the math equation pages. And as you can imagine, it's a proofreading nightmare. So we've been very careful to try to get it right. And we'd like your input. We have 2 more sections of 30 pages each in their handwritten version. And we're thinking about scanning them and just adding them as an appendix. But we'll talk I appreciate your advice on that. So this gives you a sense of his handwriting there. I think, this is the Lunar Module simulator. And this is the piece that we're putting together. This is for the telescope. And we're putting together one of the side window visual systems. And now it says, show Watson capstone video. Okay, Jack, you're up.
I'll have to shift the screen share.
So I'll stop. So this was like a Watson School senior project. They put together, their task was to put together a reassembly plan to show us how to put one of these things back together. And we should be ready to go, hopefully.
Is it all there?
Yep.
Okay.
Yep.
Here we go.
Techworks is unique. Nowhere else on Earth will you be able to see how NASA trained astronauts to fly to the moon and back in the Apollo missions of the 1960s. Today's space missions are the direct descendants of those missions, but now they use 21st century tools and technologies to meet the challenges of exploring unknown worlds. At Techworks, you will find the technologies that started it all. Here, you will be able to see the electronics and hardware that help humans succeed at one of the most difficult and complex challenges imaginable, sending astronauts to another world and bringing them home safely. No matter where humans explore in space, the technology changes, the laws of physics remain the same, and the steps are the same. Plan, train, fly, and explore. And I'm Frank Hughes, and I'd like to tell you a little bit about the training for space flights. How do we prepare astronauts for the journey into space? In the 1960s and 1970s, engineers built mission simulators, full-scale spacecraft surrounded by massive optical visual systems. These allowed astronauts and ground controllers to safely prepare for the dangers they would face while operating spacecraft, navigating, fixing malfunctions, and responding to crisis situations. These simulators were built 5 years before digital imaging existed, and even before video games existed. In Techworks, you will see how Apollo astronauts learn to navigate by the stars. Mirror reflections of ball bearings embedded in black spheres generated the three-dimensional star field so perfectly that astronauts called it the next best thing to looking out the spacecraft window.
Hello, my name is John Burke. In my senior year in the Mechanical Engineering Department at Binghamton University, I was the team lead for the Binghamton University Mechanical Engineering Senior Design Project while working at Techworks on the reassembly plan for part of the Apollo simulators that supported the astronaut training that Frank Hughes discussed.
Hello, I'm Hassan Anarklo. I, Jeffrey Taylor, and Jalal Taylor were also senior mechanical engineering majors that with John made up the student team that took on the first phase of the reassembly program. After graduation from Binghamton University, I took a position as a mechanical engineer at Richards Manufacturing Company. Here's the photograph of the Apollo training simulators at Houston. The Apollo astronauts used the simulation facility to train in the use of the command module at the far end in tan color, and the lunar module in the green color. This facility was designed and built by General Precision Lake of Binghamton, New York. Components of the simulators were assembled and tested at the Binghamton Airport. The National Air and Space Museum has launched to Techworks components of the Lunar Module Simulator Visual System. In particular, components of the Lunar Module Simulator side window. The visual system uses various optical and mechanical systems to project astronauts what the astronauts would see in the windows of the Lunar Module. This includes the starfield and Earth as they travel from the Earth to the Moon. For training landing on the Moon, a simulated view of the lunar landscape is projected as the Lunar Module simulates descending and landing the Moon. The assembled Lunar Module side window display will be on exhibit at Techworks. The showcase is divided into separate halls and galleries focusing on different local technologies. The Out of This World Technology Gallery focuses on air and space flight. The gallery will highlight the contributions of the numerous local companies to the Apollo space program. Next, Jack is going to talk about the Techworks project we worked on.
Thank you, Sam. Here, we zoom in on the side window visual system. The side window visual system projects an image of the astronaut in training would see out of their lunar module window. There are two of these systems, one for each astronaut in the lunar module. Our project was the first to accept in reassembling and exhibiting the side window visual system at the Techworks Out of This World Technology Gallery. Our project recreated a 3D model of the side window visual system and designed a supporting cradle that the side window visual system will be mounted on. The side window visual system is made up of 4 large parts. This is the beam splitter collimator laying on its left side. The beam splitter collimator is the base and has several large mirrors and beam splitters. The beam splitter collimator combines images from multiple sources and produces the image that the astronaut sees through the viewing window. The dimensions of the beam splitter collimator are 6¼ feet by 7½ feet by 8½ feet. The Stonewall Assembly is the topmost component. At the top of the Stonewall Assembly is the star ball, a non-reflective black sphere embedded with polished ball bearings arranged on the sphere in a patterned star field. Bright light source reflects off the ball bearings while the sphere is rotated to the proper orientation to show the star pattern that the astronaut would see as he flies to the moon. The simulated star field image is fed into the beam splitter collimator. The dimensions of the star ball are roughly 8½ feet by 7½ feet by 7½ feet. The occulting device provides the bright light source and controls the portion of the light that illuminates the star ball and the star ball assembly. This image on a portion of the star field image is not visible to the astronauts due to the shadow of the sun by the Earth. The dimensions of the occulting device are roughly 3.1 feet by 5 feet by 3.5 feet. The CRT display feeds into the beam splitter collimator, either an image of the lunar landscape as the lunar module is landing, or an image of the command module as it docks with the lunar module. The dimensions of the CRT display are roughly 4 feet by 3.5 feet by 3.3 feet. Now Hassan will describe the details of the project's objectives.
Here are the 4 members of the team making an initial assessment of the beam splitter collimator. The team had 2 project objectives. The first objective was to create an accurate 3D model that can be manipulated in computer-aided design, or CAD software. The 3D model supports the planning for reassembly of the side window visual system components. We call this the stack. The second objective was to design a supporting cradle that we call the stand that will support the stack on exhibit. The team spent many days at Techworks examining the components and making detailed measurements. Much of the detailed work was done at Techworks, as Jack will describe.
The detailed measurements of the components were entered into computer-aided design modeling software. While working together, the team created the 3D model of each component. The sub-assemblies, as large as those in the stack, the team had to work together to attain even the easiest of measurements. Once each component was modeled, the team then combined all of the components into a complete 3D model of the stack. Hassan will now show you the product of the hard work everyone put into this project.
Here's the completed model of the stack. The dark triangular geometry you see is the window that the astronauts view. The stack is over 16 feet tall and occupies a 10 by 10 footprint. With the model of the stack complete, the team designed and analyzed a stand that will support the stack in the out-of-this-world technology gallery. The stands went through extensive analysis to ensure that it would safely support the stack. Here's the assembled stack and stand. Within the stack, there are large mirrors and beam splitters that combine and guide the images of the stars, Earth, Sun, and the lunar surface to the window that displays the images to the astronauts as they train to fly to and land on the moon.
Hassan and I would like to leave you with some thoughts about our experience on this project at Techworks. We worked with a wide combination of Techworks volunteers, ex-NASA engineers, Binghamton University faculty, and students. This mix of experience, technical knowledge, and creative thinking created an atmosphere where everyone contributed in their unique way. Concerns to be addressed were brought to the team, ideas were generated to resolve said concerns, and concepts were introduced that assist in the process of our analysis and creating our deliverables. The 2 standout factors of our passion project were working with an organization outside the university, and then we'd be teaming up with a manufacturing company to build the stand. I was very excited to start this project as we were going to be working both in the real world. The knowledge and experience gained by working with a mix of Techworks volunteers and supporting organizations was something we would not have had just working with the university. Secondly, by teaming with a manufacturing company that will fabricate the stand, we could really focus on the design and analysis aspects to create our best work, while also collaborating with the manufacturing professionals to make sure that our design was up to industry standards. On top of this, it was highly motivating that our design of the stand will be an important part of exhibiting the Smithsonian Apollo program artifacts of historical importance.
When we started the project, the biggest challenge we faced was determining how we were going to approach the project. We found there was no source material like drawings or reports to obtain critical technical information. This led to discussions on how to obtain the measurements needed to create the 3D model and then design and analyze the stand. We decided to directly measure the components to an accuracy of 1/16 of an inch. With this data, we were able to create a 3D model to a high degree of accuracy. With that 3D model, we not only were able to design and analyze the stand, but Techworks can also use the model for other exhibits and presentations. What did we learn from our experience? It may sound cliche, but we truly feel we gained valuable experience and insight that will help us in our future professions. We learned of the power of a diverse team of people with very different backgrounds. A diverse team brings different points of view, a wide range of knowledge and experience to bear. We also learned the importance of group dynamics in a well-functioning team. What we hope that you get from our presentation is a feeling of motivation and excitement that we experienced. We hope that you will tackle projects that you might feel is a little out of your comfort zone, but provides the opportunity to learn from the knowledge and experience of others. Ultimately, the satisfaction of working on a hard problem and bringing it to a successful end.
The evolved technology at Techworks can inspire the next generation of creative thinkers to design and build spacecraft that can be flown to worlds light years away. No one person, no one company, and no one government agency could have planned and executed a successful space mission.
And it will take a dedicated team of people like you to realize the vision of Techworks. Whether you bring your time, your skills, your ideas, or your donation, you can help kindle the spirit of exploration in the next generation. Come join us on our 21st century journey to inspire by example. At Techworks, your participation has galactic impact.
Yeah.
Yeah. So is that, can you go there and look through this thing in action? Oops.
Okay, where is Susan now? Susan, you there?
Muted.
Yeah, you have to unmute before I can unshare before I can share.
Yeah, I'm stopping that now.
There we go. Oop, now I can. Bye. Okay, there we are.
I have a question.
What kind of question? Okay.
Sure.
Is this thing operational? Can you go there and look through this thing in motion?
No, it's in the process. The challenge is it's very, very large and we have to repair. There's only one area in our building where it will fit and we have to fix that roof first. So the goal is, the plan and strategy is the roof gets repaired now. The Smithsonian has to approve the reassembly plan, and the goal is to have that the roof done, the lunar module reassembled, plus the other pieces, the starball works and the telescope works, so that we can celebrate the 50th anniversary of Apollo 17 in December of this year. So that's the timeline.
Okay.
But it's approximately a $20,000 project just for the reassembly of the Lunar Module simulator. There's a fair amount of steel involved. So that's what right now we're fundraising for that. But yes, and the Starball, the Starball for the overhead window is already operational, as the and the telescope were so the Starballs the size of the Starball has to do with the size of the window. Since the telescope is about that big in diameter, this big in diameter, the Starball is only 12 inches in diameter. And that's almost ready to go. We're missing one optical piece, a relay, but once we get that done, you'll be able to look through a telescope, and that's where Al Nagler comes in. He worked on the telescope end of the Lunar Module visual systems. So that's the plan, that you'll be able to look through a telescope. You'll be able to see stars in 3 dimensions. You'll be able to see the Starball move and choose a date or a time, and then visit the side window to see how it all works, how it all fits together. So that's the goal, but come back. You want to see that in operation, I would say December of 2022 would be your best bet, but not yet, but it's on its way. It's a
No trip.
Yeah.
But we can, if you do come to visit, I'm not sure I can go down to my next. You can fly a simulator. You can fly a pilot simulator. For some reason, there you go. That I can go backwards, I think. Those the flight simulators, the pilot trains on the left-hand side are operational. They're flyable, and then you'll see a white screen in the back right-hand side. That's a helicopter visual system, a marine helicopter visual system done by Lockheed Martin in Owego. So all of those are ready to go, but we're waiting to finish the roof before we move them all into, do the math. So right now the simulated workshop is in the far right corner where it says Link Aviation Workshop, but the darker teal area is the Out of This World Technology Gallery, where the Apollo will move into, the simulators will move into, and as well as some demonstration of the inertial navigation and fly-by-wire flight control systems that come out of GE Westover, which is not far from Binghamton. So it's a general avionics and flight gallery is going in that teal area. So that's the strategy. But at the moment, we have a very, very large hole in the roof, so nothing is going in there right now. So that's our challenge for now. Let's see what really quickly that brings we vintage ice cream factory, which you'll see on the bottom right with a really rotten entrance. And on the top is our plan with an energy exhibit in the entrance. And on the Riverview Terrace, you get a wonderful view of the Shenango River and downtown. And under the Riverview Terrace is where the Out of This World Technology Gallery comes. This will, we're trying to figure out a way to highlight the Saturn V instrument unit. We don't, even if one existed, we don't want one. It's too big. We've done our fair share of large projects at the moment, but that is 22 feet in diameter and approximately 6 feet tall. And there's not any, fortunately for us, there is not one available for us to get. But we will be then highlighting the Ansco film and the Tony Sale Award and this. So these are all the kinds of things that are going to go into the gallery. And this gives you a flavor of how we approach the world. These are holiday cards from over the years. You might get a kick out of the one in the lower right. that is formatted like a stereo pair so that you can use a Civil War era stereo viewer and see the moon and the LEM in 3D. And on the right with the red bow is the Saturn instrument unit from Owego. And the stars in the middle, that's to highlight Universal Instruments, which pioneered automatic electronic insertion technologies. So that's there. And up on the top is our idea shed. It goes from Cooperstown to the Pennsylvania and Ohio border. And the heart is where we focus our energies, but we're interested in anything that comes from that region. We like to say that our only filter is geography. Any technology, any period, any product, any company, as long as it has roots in central New York State. So this is how you get in touch with me or with us. It's really a big team. It's a team effort, and we're always looking for additional volunteers. You need not come in person. Much of our volunteering over the last 2 years has been done remotely, and we have a fair amount of research and thinking projects that we would welcome your input on and welcome your advice. Our, as someone mentioned in the chat, Al Nagler is one of our big supporters, as well as his comrade from Ferrand, Matt Baum, and Martin Schenker helped us out while he was still alive, but he unfortunately passed away. So now is the time to do this. Next Thursday, 2 days from now, a 94-year-old gentleman, Gene Abbey, who led Link's mission simulator contracts, will be speaking about how Link got into the space exploration simulation mode. And that I will make sure I can send a link. It's sponsored by the American Society for Quality's Binghamton chapter, and I can send a link for that. Oh, this is something that we were not fast enough. This the technology of the simulation, as you saw, was the star balls and the reflection off the star balls. But to do landing on the moon, to do, you needed to have a different approach. So they had a 3D model of the surface of the moon and small models of the spacecraft. And then those were television, there was a television feed that went into the side window. Unfortunately, this was the last surviving surface moonscape and it was from Apollo 15, and it was slated to come to Binghamton, but during the pandemic, it fell off the wall in a hurricane damaged building in Florida, and they just swept it up and threw it away because it was a pandemic, so there was nobody to call. So when we went to NASA and said, okay, we're ready, and they kept, yeah, I'm sorry about that. So, but this is a scale of 1,000 to 1. And this is how they used to view, to learn to, as it were, navigate on the surface of the moon. And this is what it would have looked like in the simulator, facing down with the television camera. And that fed into the optics of the window. And I don't know if this helps or hinders, and we can stop if you want, but this is how the optics work. So the circle you see on the right, on the upper right, is the star ball, and then that rotates in 2 dimensions with a motor. And all of our star balls now operate. We've been able to get the electronics in that working. The curved surfaces are reflective front surface mirrors, and they do the collimation. They collimate the light, and then the flat lines that you see that are sort of double lined, those are the beam splitters. And the optical designers can say what percentage of light they want to go through and come out, but generally speaking, it's 50-50. Half of the light goes through and half of the light comes back. And that's where you get your 3-dimensional aspects of it. So that's a little bit how that works. And then the occulting assembly, the gentleman who's speaking Thursday night, he likes to call it the window shade. So the point of the occulting assembly is to change the amount of light that is illuminating the star ball. So that then simulates, you know, how much light you're getting. So it's an interesting approach there. Let's see what else I have. Now, if you're interested in the history of the Link company, it started at Link in the 1920s, and it was at L3 until very recently, and now it's been purchased by CAE Systems, Canadian Aerospace Engineering Systems, but it's still primarily based now in Arlington, Texas, with the B2 and a few other pieces being done here still in Binghamton. So, but Binghamton is by far is the home of flight simulation innovation in the United States. Right down the street. What's next? Oh, oops. Yeah, that's right. There's nothing. Oh, yeah, that's right. I think we're almost out of time, but I'm happy to answer any questions and engage you in a conversation. But we are very, I forgot. I'll stop sharing my screen so that can you all see what I'm holding up?
Yes.
It's hard for me to tell. But it has the inner circle is inscribed with lines and then Roman numerals. And then it has a piece of metal that goes from here, which perhaps is a gnomon. And then this whole thing rotates back and forth. And it has on the foot, if I don't drop it, it has a plaque very similar to what was left on the foot of the LEM that's on the moon. So, yeah. So we're very curious. It came from one of the Link engineers' estates. He worked on the visual system, but we're not sure what it is, where it came from, or how that works. So we're interested.
Yeah, very nice.
Give me that.
That was wonderful. Oh my goodness. Can't wait to get up there to Binghamton.
Yeah, come visit. We're flying. Things are flying. The vintage IBM Computing Center is in full operation. You can always use a typewriter, but in addition, we have some of the early Link. Oh, this is me, sorry. We have an early Link piano. We have a Nickelodeon, and for better or for worse, we just acquired a silent movie era Link organ. And so they had some very special technology for theme music that go with the projector in the silent movie era. The projectionist would just only show the film. He would have a series of endless rolls, and he could pick romantic music, you know, parade music, Indians coming, war music. And so we just recently acquired, there are two left, and we have one of them. So, but that will not be operational for a while. It's going to take us 5 years. Oh, good. Thanks. Oh, somebody from Copernic. Yes. Copernic's not far away. It's up the hill. Yeah.
Very, very nice. Any questions for Susan on the Zoom session?
Great.
Outstanding.
And mark your calendars for the end of December. We hope to do something for Apollo 17, but we're not quite sure what that will be yet, but it will be something.
Outstanding. That would be great.
Yes.
If we have a finished roof, it'll be bigger than if we don't have a finished roof, it'll be smaller. Thank you for your time, and thank you for your interest in what we're doing. And again, if we can do if we can excite you or give you, if you need a project, we've got plenty to share.
So I do have a question. You have students working on this one project,
do you have, would it be beneficial to have another group of students available, or do you have enough labor to help you with such things?
Oh, we have our to-do list is longer than our volunteer list. So absolutely, we're interested in students. And over the past 2 years, we've developed, they can do on-site or they can do virtual online. So
Okay.
we can make both work. Yep.
Well, we're here at SUNY New Paltz, where I teach physics, and our engineering program has something similar to what the BU students did. It's called Engineering Senior Design, and a group of them take on a task for either, sometimes they call them the customer or they call them the shareholder, but they have some kind of goal. Now, what you have to do is write up some kind of explanation of what the goal of the project is. And at the beginning, it's a year-long class. And at the very beginning, they choose what project they are interested in. Okay. So I've proposed several projects, and sometimes they are interested and sometimes they pass. Right. So there's no guarantee, but we could arrange to perhaps have you present some projects with our department to see if we could attract one of these teams to your.
We'd be very interested. We've been working with the Watson School since 2005, I believe, on projects. And what we're flabbergasted about is their inability to solder. So we can't.
I teach our physics students how to solder, so I will make sure that our engineering students know how to solder too.
All right. Well, then, if you've got students who can solder, they're top of our list because.
Okay. I'm going to pass that on because
seriously.
We have a new workshop in our basement that's been christened the Steam Lab, or Steam Ship, I'm sorry. Steam Shop. It's supposed to be a pun on steamship. Okay. Steam, of course, is science technology. Anyway, but yeah, I will make sure they all know how to solder and do more than that. So,
but let me just, initially, the requirements from the university were that it had to end in a physical product. Right. So they had to make something. And what we were flabbergasted about is they had students for 3 years where they never allowed them to do anything. And then all of a sudden for their final project, they had to create something. And it's been a struggle. So what we found is the mechanical engineering students are more likely to deliver. And we've also been reasonably successful in convincing the university that 3D drawing you saw of the visual system, that's a product. Yeah, it took us a while to get but we have to be creative in terms of fitting what we need into what the students can do. But we'd be delighted to talk to you about it and strategize. Let's talk early, and then we'll come up with a project or two.
Okay, I'll get your contact info and follow up, and we can at least put something into the mix. I'm competing with them too for other projects, and we'll see if we can get a team interested.
Right. And if your university does not require a physical model, then we have even more projects for them to do.
I'm not in that department, but and I did one where they were going to build a robotic arm for basically a selfie stick for a high altitude camera, high altitude balloon, a camera on a balloon. And COVID hit, and so they were going to allow them to do the drawings and everything, but they actually together, separately, working in their apartments, they all built a little mechanism that at least could deploy the camera. So they built something.
Right, excellent, excellent. Right, well, so we're as interested in there's ideas and then doing calculations feasibility kinds of calculations or stability, those kinds of things, as we are they're building something. That's a challenge for this generation of actually creating a physical.
Yes.
And we'd like to fix that, but not at the expense of unique artifacts. Just as an FYI, 2 lunar module simulators, 2 of the green parts were built and 3 of the brown parts were built. So there were 2 complete Apollo mission simulators, of which 1 has survived. And there was an extra command module simulator, so they could start practicing on how to fly or drive, if you will, first, before they got into the learning to rendezvous and dock. So yeah, so we have to be extremely careful how much touching anyone, let alone students, can do when we're working with things like that. Now, it's rare. I doubt we'll get anything else that's quite as unusual and as rare as that, but you never know. So, but we'd be very interested in working with you. Yep. Oh, there's some big chat. Hold on, chat.
That was mostly, I think, Alex asking Art if,
I couldn't do it to just him. It wouldn't let me talk to only him.
Oh, well,
Sorry.
that's okay. That's usually selection. We'll go over that later. Any other questions? That was absolutely wonderful. Marvelously fascinating.
Yeah.
So new.
Very good. Thank
Just
you
a
again so much, Susan. Thank you so much.
You're very welcome. And again, it's a reflection of the enormous creativity of this community. You know, that's, I just reflect what we see around us. So thank you very much for having us. And
Absolutely. Thank you for speaking. All right. Once again, for those who are local, we'll dismiss here and go to the pizza place.